Good evening, everyone. Today our topic is practical exploitations on Zigbee class networks. The agenda is, first we will understand what is IoT ecosystem. Then we talk about building blocks of IoT ecosystem. In particular, we have selected communication protocols and specifically Zigbee style network. Today we have some cool demos on how to sniff and inject packets in the Zigbee network. We have devices called as RZ USB stick. We will be using this to inject and sniff the packets. At last, we conclude our presentation with the SDLC, that is Security Development Lifecycle for IoT ecosystems. Regarding us, my name is Sunil. I am Principal Security Analyst in DeepArmor. He is Nitin Lakshmanan. He is also a Principal Security Analyst in DeepArmor. Regarding DeepArmor, we are a security firm where we do vulnerability testing, penetration testing for the cloud, mobile applications and the IoT products. Apart from this, we also provide SDLC and cloud trainings for various organizations. Let's jump into technical sections now. This is how a IoT ecosystem looks like in general. It mainly consists of 4 components. First is cloud, second is mobile, third is hardware devices, and mainly the important one, the fourth one is communication protocols. Let's take an example of home automation system. In the home automation system, we will be having a nodes which collects the sensor values like temperature, security alarm and more. At regular intervals, these nodes will send the information to the gateway that is deployed in the house. It will be using the lightweight protocols like Zigbee, Z-Wave, RF signals. Once the data is received by the gateway will be sending information to the cloud through the HTTP protocols. Cloud, which has the larger competency power, it will store all the sensor values and it even manages the user management details and sometimes multi-tenancy architecture as well. There are mainly 2 types of cloud. One is private cloud and one is the public one. Public one, we already know that there are few popular providers like AWS, GCP and Azure. Next component is the mobile component, where the user can log in into the application and he can see the home status at any given point. This can be also used to configure the gateways, like if there is a temperature more than 25 degrees, there should be an alarm so that the user should come to know. So the mobile application can be used to configure the gateway through the protocols like Bluetooth, BLE. There are different types of IoT systems. Few of them are medical healthcare IoT, consumer IoT, industrial IoT and the home automation IoT. Today we are focusing on industrial IoT because Zigbee class protocols are mainly used in the industrial IoT. This is a bigger IoT space where we'll have a multiple gateway devices, nodes in the environments like asset tracking, agriculture, smart metering and more. IoT plays a very important role in the industrial area because it will be used to identify inefficiency and defective products in the early stage itself. So by knowing these things, manufacturer can reduce their cost and time. There are few challenges in industrial IoT, such as like these devices sometimes may need to be deployed in a remote area where access to these devices will be very less. So the deployment should be done in one shot and it should be perfect. And other few challenges are like these devices will be of very less memory. It will be having a less memory and implementing security features like public key, crypto, secure boot, and it will be quite difficult in implementing these security features. So we know this is the IoT ecosystem, but where a problem can exist in this system. It can be anywhere in any component. It can be in the cloud through the API missecurity or cloud misconfigurations. It can be in the mobile through the insecure storage, or it can be in the devices because of weak secure boot implementation or the firmware over the air implementation. And at last, the protocol. It can even exist in the protocol because we have seen multiple cases where manufacturers fail to implement good security measurements for their protocols. Even though the protocols comes with few security measurements, the manufacturers will not implement those things because of the constraints in the IoT devices. So let's talk more about the communication channel and the issues there. This is the blueprint of how communication happens in the IoT product. You can see there are multiple protocols involved in the components. Like it can be HTTP protocol between cloud and gateway, cloud and mobile, or it can be Bluetooth BLE between the mobile and the gateway. And then comes the IoT protocols, lightweight protocols or low power consumption protocols. Usually this will be happening between the IoT devices. Now we know that there are devices like gateway and the node. So between these between these devices, the lightweight protocols will be used. Selection of IoT protocol plays a vital role in the product because there are challenges like flexibility of the protocol and the security measurements in the protocol. So the designer or the manufacturer should be very careful in selecting IoT protocols for their product. When you just search for IoT protocols in the Google, you will be ending up with some 20 plus protocols. So choosing the proper protocol will be a difficult task for manufacturer. There are protocols like LTE, MQTT, COAP, Zigbee, BLE. Out of all these protocols, today we are mainly focusing on Zigbee. So before understanding the Zigbee protocol, we need to understand 802.15.4 IEEE standard because Zigbee is an extension of this particular standard. This is a IEEE standard for mainly low rate wireless personal area networks because the power used or the energy used in sending the data in the IEEE 802.15.4 standard is very less because the duty cycle to transmit the packets will be very less. And it mainly modifies the physical and media access control layer in the ISO model. Physical layer, it defines the frequency, in what frequency the protocol should work, whereas in the MAC layer, it defines the mesh architecture and the message format. As I earlier mentioned, the Zigbee is an extension of this standard and it mainly operates at the layers above the MAC layer. It improves the security and the mesh topology so that it can be used for any product. Zigbee is widely used in the industrial IoT. Apart from that, it is also used in smart energy medical IoT sector as well. It operates at 2.4 gigahertz and sub gigahertz, and as I mentioned earlier, it consumes very less energy and manufacturers need not worry about the batteries because the battery will run for years and years. And it is less expensive when compared with the Bluetooth, and it can be operating between the 10 to 100 meters based on the product requirement. Zigbee comes with few security measurements because the communication between the devices should be encrypted. There are mainly three keys involved in Zigbee protocol. The first one is network key, where the communication happens with this key, because whenever the node sends messages to the gateway or the gateway sends messages to the node, it will be encrypted using the network key. And when the node joins the network, it should receive a network key and in the encrypted format. That will be done using the trust center link key. Whenever node joins, encrypted network key will be sent to the node. Last one is a link key. It is used for encrypting the unicast communication. If a particular node wants to talk with the with the gateway, at that time link key will be used. There are mainly three phases in the Zigbee standards. One is before Zigbee Pro, second one is Zigbee Pro and Zigbee 2.0 or 3.0. With each phase, the security has been drastically increased. Like for example, in before Zigbee Pro, there was no trust center link key, and as trust center link key was not there, the network key was transmitted in a plain text way. So anybody in the vicinity of the network can sniff the traffic. So with the Zigbee Pro and Zigbee 2.0, the trust center link key has been introduced and the network key was encrypted and sent to the node. There was no replay protection in the before Zigbee Pro, but it was implemented in the next versions. Similarly, there was no integrity protection in the before Zigbee Pro, but in the next phases, it has been implemented by adding 128 message indication code in the packets. let's jump into the attacking scenarios and the demos. Before that, we will be giving the overview of how the system looks like. So today we are using 2 machines, and we will be using the Harzi USB sticks to generate the packets, Zigbee-like packets. It is just a simulator today we are showing, and not the real products here. And we will be sniffing, we will be injecting the packets, and we are using a Python module called as Scapy to modify the packets. And at last, we will be concluding our presentation on how to provide security for these kind of networks. So first, let's understand the packet structure, how a Zigbee class like packets will be. There are multiple headers. The first one is destination address, which means that the packet is generating from this particular machine, and destination is where the packet is going. Whereas in the source, it indicates that where the packet is getting generated from. The sequence number is identification number. It is used to identify the packet number. Fourth one is personal area network ID. If a group of or a collection of nodes talking to one particular gateway, at that time a particular PAN ID will be generated for that particular network. And the fifth one is payload, which is important here. Today we are using only 2 message formats for our demo purpose. The first one is DA, where the actual data will be sending, and the second one is DD packet. It means that the node has received the DA packet with the data, and node will send a DD packet as an acknowledgement message. Last one is frame checks sequence. It means Zigbee has come with a checksum implementation, and it will add a 2 bytes checksum at the end of the packet. I will be handing it over to Nitin.
Good evening, guys. So this is how the wireless sensor network looks like for our demo today. So we have a gateway, a node. The gateway and node are going to communicate between each other. So the gateway will be sending DA packets, which are custom packets, which will have a set of instructions for the node to process it. So the node will receive this packet, process it, and send back a reply like an acknowledgement in the form of DD packets. So there is also a third element in this scenario, that is the attacker, who is going to inject and sniff into this network. He will be in the vicinity of the gateway and the node module. So let's see what can be done. So for today's demo, we are going to concentrate on sequence number and the payload. As when an attacker manipulates the sequence number, it will be possible for him to create replay attacks. And when the payload is modified, it can manipulate the entire network. For example, if you take a vaccine transport mechanism where the temperature of the vaccine and the container should be maintained, an attacker injects a different temperature so that the vaccines become lethal. This is what we are trying to do today. So for this demo, we are going to use 3 RZ USB sticks developed by Microchip. We will have 2 as victims, that is the gateway and the node, and a single RZ USB stick as an attacker. So we use Killer Bee framework, which is developed by Riverloop Security. It is one of the 802.15.4 exploiting and exploration tool. And along with that, we have 17 tools in Killer Bee. In that, we are going to use Zigbee Wireshark and Zigbee Replay. And we will be using Scapy. It's a network packet creator, manipulator, everything. So thanks to all the developers of these tools, which was very helpful in developing this and studying about these protocols. So this is how the setup looks like for today's demo. So we are going to have one machine connected to 2 RZ USB sticks. So the first machine here will act as the victim, that is the attacker and gateway and node. And the second machine which we have over here will act as an attacker. So let's get into the first scenario where we inject packets and sniff the packets. So for today's demo, this machine is going to act as gateway, and this particular RZ USB stick is going to be the gateway. And one more RZ is will act as a thermostat. Like it will receive temperature from the gateway, and it will change the temperature of the environment to the mentioned temperature, and it will send back a DD packet if it accepts. So in this vicinity, there is another RZ USB stick which acts as an attacker. He will try to sniff this traffic inject. Let's see what happens in those scenarios.
So we have two windows here. The left one is gateway, whereas the right one is the node. So as we have connected two RZ USB to the same machine, there will be two IDs for this RZ USB. So to identify the RZ IDs, there is a command called as Zigbee ID. When we enter this command, we will be getting two IDs displayed here. You can see that the first ID is 14, the second one is 15. 14 will be using it as gateway, whereas 15 will be using it as node. So in the beginning or at any stage of the point, the node will be always listening for the gateway packets. So first we will start node to listen to the packets. So for that, Killer Bee framework has provided a command called as Zigbee Wireshark. So, and one more thing is Zigbee like protocols will be working at different channels. We are selecting channel 21 for our demo today. As I earlier mentioned, we are using 15 as the node. So I need to provide the ID number here. So when we enter the Zigbee Wireshark command, a Wireshark terminal will be opening, and here whenever there is a packet called Zigbee packets, it will be capturing it here. So now node is listening for the traffic. The gateway will be sending a DA packet with the temperature value as 13. There is a command called as Zigbee replay. It is used to send the packets in the Zigbee network. So we are using that command, and we are sending a gateway packet with the temperature value. We are using 14 as the gateway, so I am providing the ID as 14 here. At the same time, the attacker is also listening in the network, so we are starting the same Zigbee Wireshark command in the other machine. So by executing the command Zigbee replay, a packet has been transmitted here, and we should be able to see it in the now we have received a packet in the Wireshark. And you can see that the packet contains a value called as DA0113. It may indicate that this is a DA packet. So we are exporting this packet in PCAP. So now node has received the packet, and we should see whether give us a minute. Yeah, now node has saved the packet, and for processing the packet, we have written some small Python scripts here. So by executing that Python script, this packet will be processed, and if the packet is correct, it will be updating the it will be updating the temperature to 13 and it will send a DD acknowledgement message. So the packet received is GW1. And if the packet is correct, it will send a DD acknowledgement message. So by executing this Python script, you can see that the payload is DA0113 and the packet has been accepted here. Upon accepting the packet, it is sending DD heartbeat messages. So once this is done, it means that the thermostat has set the temperature value to 13. So now we will be in the real time scenario, the node will be continuously listening for the traffic. So we will be again entering the command called as Zigbee Wireshark. So the attacker in the vicinity has captured the same packet and he will be showing how he can modify the packet here.
So I'm going to show you how to edit the packet using Scapy. So I have captured the same packet which the gateway has sent. There is a command in Scapy called read pcap. Pcap. So once we load, we will be able to see that the pointer P now represents value. So it is 13 here, XDA0113. So now I'm going to change this value to 14. And I'm going to save this packet as an attacker pcap. So now I'm going to use the same Zigbee replay tool to send a malicious packet into the channel 21. So the packet has been transmitted. Let's see how the thermostat processes this packet.
Yeah, as node was listening for the gateway packets, it has received one Zigbee packet which is from the attacker, and you can see that the temperature value here is changed to 14, DA0114. It means that we have received some packet, but node will not find out whether it is from the gateway or it is from the attacker. So we'll save this packet and we'll be processing it. Yeah, the payload is DA011445 and it has been accepted and it is sending DD packet. This is happening because the node is failing to understand whether the packet is from the legit gateway or it is from the attacker. Because there is no integrity protection and there is no way that node is not able to judge whether it is from the legit gateway. So we'll be seeing the solution now. Yeah. So we know that we need to protect payload, and there should be a way that node should identify whether it is from the gateway or not. So for that, there is a solution like a gateway and the node should be having a secure key exchange between them, and there should be some protection for the payload. For that, what we can do is we can add a HMAC calculated for the payload, and it can be appended at the end of the packet, each packet. Whenever gateway sends packet to the node, a HMAC should be sent along with the packet. Similarly, when node sends packet to the gateway, an HMAC should be appended at the end of the packet. So when gateway sends packet with the HMAC for the payload, the node should calculate the HMAC in the same way that gateway calculated, and it should compare whether the calculated HMAC and the received HMAC are same. If it is same, it should accept the packet, or else it should reject the packet. An attacker can still sift the packet, but whenever he modifies, he can't get the correct HMAC in the packet, because he will be not having the secure key that has been exchanged between the gateway and node. But there is a scenario where attacker can still inject packets and he can successfully modify the temperature of the thermostat.
So as an attacker, what I will think is as the integrity of the payload is protected, so I will be changing the sequence number of the packet. So the node thermostat will not accept the same sequence number again. So I am going to modify it to a further value which I anticipate to be the future value. And when the gateway sends a different temperature, I reset back it to the old temperature by changing the sequence number value. So now I have manipulated in a way that I have sent the same packet, but at a different time instance. So still the attack is possible. So still we can attack the environment. So here the sequence number is modified and the node accepts it because the integrity calculated for the payload is still the same. It is valid. So this is what I have explained in the previous slide. That is, in the scenario 1, we had protected only the payload, and the attacker was there was no protection. Then attacker was able to attack it using by editing the payload. Now an attacker can affect all other headers by affecting the source, destination, PAN ID, all the headers, and still cause havoc in the network.
So when only the payload part is protected, there are different scenarios that we can achieve here. As Nitin mentioned, there is a replay attack possible, which means that we are sending a same packet again and again in the network, and we are setting the same temperature throughout the journey. The second one is, as we know that source address and destination address are not part of HMAC calculation, we can spoof all the nodes in the network. For example, if there are 10 nodes in the network and the same network key is used in the WSN, at this time we can spoof all the nodes in the network. The last one is the PAN ID attack. If there are multiple PAN networks or personal area networks, and if they are using the same network key, at this time also we can spoof in all the personal area networks. So for this we are giving a solution called as full security solution. Okay, what we are proposing is like the entire packet should be HMAC protected. It means that the payload as well as the headers in the Zigbee protocol should be protected with the HMAC. So the gateway will calculate HMAC for the entire packet, and it will be appending HMAC at the end of the packet. Upon receiving this packet, node should again calculate the HMAC, and it should re-verify whether the calculated and received HMAC are same. Attacker who does not have knowledge about these things, even though if he modifies any part of the packet, he will not be getting the correct HMAC, and the node will be rejecting the packets. So we'll be seeing a demo for full security. So at first the node will be listening for the traffic in the channel 21, and we are using the same ID that we have used previously, 15. And the gateway will be sending that gateway packet, and we will be seeing what is the format of this packet now. In the channel, we are using the same channel 21. So now, as we have mentioned that there is something called as HMAC in the packet. So we'll be seeing that. You can see that now the payload has been bumped up by 16 bytes. After the DA011345, there is a 8-byte HMAC. We have truncated it for computation because of the computation issues. As there are a few Zigbee packets in the network, we are seeing multiple apart from the packets sent by the gateway here. I am saving it as GW3.pcap. Now node has received the packet and we will be executing the Python script which have HMAC calculation code. You can see that the payload is DA011345. The HMAC in the packet is this one and the calculated HMAC is same. So as the HMAC is same here, the packet has been accepted and it is sending the DD packet. So again the gateway node will be listening for the traffic and attacker who has captured the same HMAC protected packet, you will be modifying the sequence number and you will be sending it now.
So I have modified the sequence number now and I'm going to replay the same packet to the thermostat.
Previously the sequence number was 45, I think I forgot to show it, but now attacker has modified the sequence number to 50 and we will be seeing whether the packet will be accepted by the node or not. So now I ran the Python script for the gateway 3 packet which has the sequence number modified. So the it is not coming now. Yeah, the payload is the same DA011345 but the sequence number was modified. So the calculated HMAC is different from the received HMAC. So the HMAC verification has failed and no DD packet has sent. That means that now the node is able to identify whether the packet is from the genuine or the legit gateway or it is from the attacker. So to harden the Zigbee style networks, the complete packet should be integrity protected, and we are mainly saying that it should be integrity protected but not the encryption, because nobody cares whether the temperature is 13 or 14, but they care that it is set by the legit gateway or not. So it should be integrity protected rather than the encryption. So what we are now we are proposing a security development lifecycle approach for the IoT products. We have seen a different scenarios, like like only the cloud architecture will be undergoing the security assessment, but not the complete SDLC complete 4 components. So what we are proposing is 5-step approach for IoT security. It runs from S1 to S5. In the S1 phase, we identify the key attributes like what are the assets of the product, what are the main security objectives of the product. Whereas in the second phase, which is threat modeling, for each security requirements derived from the S1, we identify the threats and the threat vectors. And these threat vectors will be nothing but the pen testing cases in the 4th phase, which is penetration testing phase. S3 is the focused security code review phase, where we do a code review audit or run some security tools, security code tools on the code. 4th one is a penetration testing phase or the fuzzing phase. It is a important phase where we identify actual vulnerabilities in the product, and output of this phase will be a security report with bunch of vulnerabilities. Last one is the fix verification. Upon fixing each security vulnerability, we will be verifying whether the fix is adequate or not. And if there are any new features implemented in the product, it should undergo the delta security model. If required, it should go from S1 to S5. If it is small changes, based on the changes, we should identify whether S4 is only required or S2 is also required. And this particular SDLC model should be applied for each component, and even it should be applied when 4 components which are mobile hardware and the cloud, when they are integrated, we should do the complete SDLC procedure again. And one more important thing is we should follow the shift left policy, which means that security should be integrated from the beginning phase itself. Even from the design phase, the security engineers should be involved in the meetings to identify the issues in the beginning phase itself. You can see that the security issue identified in the first phase, S1 phase, will cost you few $1,000, but it can shoot up to millions of dollars when it is identified in the post-production phase. Yeah. We are going to summarize now. What we are trying to say is include security in all the components, and even we should do the security assessment when these 3 components are integrated, because we have seen some interoperability issues also. So we will be talking more about interoperability issues in the tomorrow's presentation that will be given by Nitin. Yeah. Are there any questions regarding this?
But first of all, thank you very much, Sunil and Nitin. Please give them a big round of applause. Yes, well, is there any question?
Thank you for your presentation. How are you able to capture packet if you don't have the network key of the Zigbee, or did I miss something?
So the 802.15.4 just publishes the packets in the particular channel. So anyone who is sniffing in the same channel will be able to capture the packets.
Okay, so the payload isn't encrypted by the network key.
Yeah, for this custom packet, it's not encrypted. Only integrity is maintained.
Thanks for the talk. In any commercial project, have you ever seen this kind of stuff happen, like not using any integrity checks, like in known projects?
Yeah, actually, there were some products which were not protected like this. Then we were able to give the solution for this, and then we have redesigned the product itself. Thanks.
Any more questions? Well, thanks again, guys. Great talk.
Thank you.
Thank you very much.